Okay. I'm recording now, Heidi. So you can leave whenever you want and it'll be posted right after. Okay, so yeah. So these are all technically resonant structures of cyanide. The most stable resonance structure is the one with the least amount of formal charges. In this case, would be these two. Um, but I'm pretty sure, I don't actually know this exactly, but I'm pretty sure this one's more stable just because um, carbon holds the negative charge a little bit better than nitrogen. Um, yeah, both of these are right though. So like, don't stress about that because if there's resonance structures, there's like not always, and these have the same amount of formal charges, right? They both have a negative one. So they're both technically more stable. Um, yeah. Sorry. Does that answer your question, Jackson? Cool.
But pretty much for all intents and purposes of this test, just remember that first one.
Yeah,
Like,
yeah. That's this is
okay.
correct. So if you're memorizing it, that's correct.
Okay.
Um, and if you want to play around, if it does ask to draw like resonance structures, which um yeah, if it does ask to draw resonance structures, then like just play around with the double bonds, make sure you have the right amount of electrons and make sure you're signing the right formal charges, and then you're fine. So cool. Make sense? Cyanide. Hydroxide. Hydroxide is OH minus. So this one just looks like this. O bonded to H. O has a negative charge. This one's really simple, but it's really common. Just remember hydroxide. One hydrogen, one oxygen, hydroxide, hydroxide. That's that one. So some of these you can remember like cyanide, cyanide. That's like a really unique one, just CN. Yeah. And then the carbonate ones like carbonate, phosphate, nitrate, sulfate, they all end in ate. Um, it's gonna be like sulfur with oxygens, nitrogen with oxygens, phosphorus with oxygens, carbon with oxygens. But just make sure that you have the right amount of oxygens, like you know which ones have because they all have different charges on them, different amounts of oxygen. Okay, so carbonate has three oxygens. It's CO3 2 minus. This is carbonate. So we have three oxygens. One of them is a double bond. The other two have negative charges like this. Okay. Formal charges on this. These two oxygens on here, um, they should have six valence electrons. How many do they have? They have seven. So 6 minus 7 is negative 1. So it has a negative 1 charge. Okay. Um, Here, this one is 6 minus 6 because it has six valence electrons, so charge of 0. Carbon should have 4 minus 4 equals formal charge of 0. Okay. Formal charge is kind of it's like a specific concept, but it's actually just like we're just figuring out like what's like mathematically calculating what's the charge on each of these atoms and why is it this charge. So when you look at a formal charge, usually it's 0. If there's a negative charge, it's negative 1. If it's positive charge, it's positive 1. And just being able to find that from the valence electrons um, kind of just becomes more just second nature. Again, it's pretty simple, but hopefully that's making more sense. Hydronium. Um, this one is H3. Sorry. H3O plus. Okay, so this one is an oxygen with three hydrogens on it. We have 6 on the oxygen, 3 electrons there, and then a positive charge. So I'm doing like negative 1 electron. So we have um, 8 electrons. There should be, right? So there's 5 electrons on the oxygen because there's a positive charge, and then there's 1 on each hydrogen. So let's make sure we have all our electrons. There's 8, 2, 4, 6, and then double bond, a lone pair on oxygen. This gives oxygen the formal charge. It should have 6 valence electrons. It has 1, 2, 3, 4, 5. It has 5. So 6 minus 5 equals positive 1. Okay, so there's a formal charge for oxygen. That's where our positive charge comes from. This one was just on the study guide, so I'm just like telling you what it is. This one comes a lot more. We look at these two a little bit later in the semester with acids and bases. So these are good to know and remember. Okay. Any questions about any of these? Anything else you want me to explain?
Okay, I have a random question, and this might not be like it might not correlate at all, but on hydronium, it has H3 and then O plus, and the O in the Thompson, like in the little drawing, has the plus. And then also in carbonate, CO3 2 minus, the O's are the ones that have the negative charge. So is it always like that, where like for hydroxide, for example, the OH, the H is negative, or does that just not apply to it at all?
No,
Does that
that's just how it's written. So
Okay.
yeah, you kind of have to, it's always written with the charge like up in this right corner,
Okay.
even though that doesn't, it's not saying that's the atom that has the charge. You kind of have to figure out which one has the charge, you need to draw out the Lewis structure and
Okay.
do like the math, like I was saying, right?
Yeah.
Because hydroxide, the charge is on the oxygen here, right?
Yeah.
You'll never see a negative charge on the hydrogen. So
Okay.
oxygens love negative charges. They're often there because oxygen's super electronegative. So a very electronegative atom likes more electrons, which means it's very comfortable with the negative charge, right?
Perfect.
Yeah.
Thank you.
Yeah, no worries. Okay, so what's next? Um, did anyone else have I sent the list again, so if there's any other topics you want to cover, send it in the chat. Let's do oh, did you want me to go over covalent naming or are you guys feeling good on that? If you want me to go over naming just like regular covalent, okay, let's do it. So let me pull up some practice problems. I'm gonna go to my photos. I feel like it's risky like going to my photos here because I don't know what's gonna pull up. Nothing crazy, but you never know. Okay, so these are from the practice exam. If you did it already, we're just gonna look at them again. I just thought they were really good examples that are helpful for your test. Okay, so name the following compounds. Let's do these four. Okay, so I'll walk you through the first one, and then I want you to kind of try to do the other ones yourself, and then go from there. Okay, so first one, again, that when you're naming just like a compound like this. Oh wait, these are okay. These are ions. Okay, so the ions are a little bit different. We're naming these. Let's do this. We just talked about ions. So with ions like this, you can tell it's an ion because you're looking for a cation on one side and an anion on the other side. You can usually tell this is the case when you have two atoms bonded right next to each other, and one of them is located on this side of the periodic table, which is going to be your cation. The other one is located on this side of the periodic table, which is going to be your anion. Okay, so this is like, if you're like, I don't know if these are ions, well, look at the atoms. Like, for example, magnesium chloride, MgCl2. Where's chlorine? It's right here, right? Magnesium's over here. If these two atoms are bonding to each other, the only way they're going to do that is if it's an ionic bond. Okay, because this atom, Mg, well, magnesium, it loses two electrons, right? And it becomes magnesium 2 plus. Chlorine gains an electron, becomes chlorine Cl minus, right? And then these two are going to combine. One magnesium combines with two chlorine atoms with a negative charge to balance out the charges. So then it's MgCl2. Okay, just a note on this. Remember that like it's important to know how to get your ions. Like if I were to say like what charge would be on calcium? Like what charge if calcium is ionized, meaning it either gains or loses its own electrons, what would be the charge on it after it's ionized? Okay. Remember that all atoms, they all want to be like the noble gases over here. Okay, I should really just like bring out periodic table, but yeah, they all want to be like the ones over here because they're very stable. The valence shell is very full. They all want to have the same amount of electrons, which is why chlorine is going to gain an electron to have the same amount as here. Magnesium is going to lose 2 electrons to have the same amount as this guy over here. Okay. So someone throw it in the chat. What would be the charge on calcium if it was ionized? I guess I should give you a periodic table. I should do that. Let me hold it up here. Got one somewhere. Oh, this is terrible. Where are you? There he is. No. I think it might be at my house in the closet. Okay, so here's our periodic table. What would be the charge on calcium if it was ionized? Calcium's right here if you need help. What would be the charge? Send it in the chat. 2 plus. Nice. Pretty simple. Just make sure you know how to do that. Okay. So, it gets a little more tricky when we're looking at the transition metals. Okay. Let's look at this first one, iron. Okay, so iron, and there's 2 irons, Fe2O3. Okay, so this is an ion. It's an ionic bond. The Fe is right here. Well, I shouldn't say Fe. Iron is right here. Okay, so you can't really, you don't find out, you can't count and just figure out what charge is on it because iron usually has a 2 plus charge or it'll have a 3 plus charge. It just depends. Yeah. So to find this out, oxygen, we'll start with oxygen. Well, to oxygen, what's the charge it usually has? It's right here, 1, 2. It usually has a 2 minus charge. So if there's 3 oxygens, that means the total charge on this side oxygen is creating is going to be 6 minus, right? Which means the balancing charge would have to be 6 plus. If there's 2 irons, that means iron is going to have a 3 plus charge because 3 times 2 is 6. Okay. So we're balancing out the charges here. We look, well, oxygen has a 6 minus charge. So this side needs to be balanced. So we have to make sure the iron is making an overall 6 plus charge, which is why there's 2 of them. Okay. So the name for this, how we would write this out would be iron. And then in parentheses, you put the Roman numeral 3 oxide. Okay. We're using this "ide" ending again. For anions, you do. For ions, you do it too. Okay. So iron 3 oxide. If you were to see like on the test, it showed like Cu4 or something like this, like copper 4. Okay. This means that copper has a 4 plus charge. That's what this means. Okay. So the parentheses are telling you what the charge is. Cool. If it shows you like let's say it showed you chromium and then like Cl, like say it showed you this. This is telling you that, well, Cl would give you a -1 charge because when it's ionized, it has -1. So then chromium, to balance it out, is going to have a +1 charge. Okay. So you'd have chromium +1, Cl -1. That would be the parts of the ion. Okay. And then if we were to name this again, you put the first one first, chromium, and then the charge in parentheses 1 chloride. Okay. So that's when we're naming like transition metal compounds. Yeah, any questions on that? It's kind of a niche one, but okay, yeah. So next, magnesium. I don't want to tell you. I should. Sorry. Hopefully you've had the chance. I think I already gave you a chance to write down all these ones, so I'll help you with them. MgCl, we're gonna have its magnesium, chloride. The nice thing about ions, I guess, one specific thing is you don't use the prefixes to tell you like how many there are, right? So we wouldn't say magnesium dichloride, even though it's MgCl2, right? You don't say dichloride because we don't need to, because we know how many chlorides there are just because of the charge, right? Because magnesium has a 2+ charge, we know that we need two chlorines. So there would never, like you would never have Mg with one chloride, right? It would never be like this. There would always be two. So that's why they don't use the dichloride. Okay. So I guess maybe rules for this. Always end with "ide," right? You're always going to finish oxide, chloride, fluoride. Unless it's polyatomic. Okay. And then don't use prefixes because we already know what they are because we have the charge. Okay. Okay, let's do C. We're gonna do the third one. NaNO3. Okay, so this is a polyatomic ion. This is our anion, which is the negative charge. The whole thing is our anion. And then this is our cation. Okay. So when do you use the prefixes? Use the prefixes. These are ionic compounds. So they're ionically bonded to each other. With covalently bonded compounds, that's when you use the prefixes. One example would be carbon dioxide. These are not ionically bonded to each other. This is a covalent bond, right? So it would be carbon, the first one you say first, and then two oxygens, so dioxide. You always end with the suffix "ide." Okay. And I'll do a few more of those examples after this because I think the next thing on here. Oh no, those are more. Those are just more ionic ones. So I'll give you some more covalent examples. But yeah, let's do this. NaNO3. So first one, put our cation first, sodium. And then what's this? What's this? It's going to be nitrate, sodium nitrate. Okay. So these ones are actually pretty simple. Like, don't overthink it. There's just like if it's the polyatomic ion, you have that memorized, right? You know what NO3 minus is. It's nitrate. Okay. At least I would recommend memorizing them. And if you've joined since I told you, the ones you want to memorize are all the ones that are on the study guide. Okay, so look at the test study guide, and the polyatomic ions that are listed on there are the ones you want to memorize. Sulfate, phosphate, nitrate, carbonate, cyanide. There's 8 of them. Okay, so it's not too bad. What was I doing? Oh yeah, next one. Sorry, I always erase everything. I'm sorry for doing that because I know some people are still writing things down. Na2O. Okay, so we're balancing out the charges here. Sodium has a plus charge, but there's 2 of them. So we have 2+ on this side. Oxygen usually has a 2- charge. So it's balanced. Sodium oxide, right? Just the same thing. Okay. Balancing the charges comes in handy when you're given this problem like this, where it gives you the name and then you're supposed to draw out like the symbol. For example, potassium phosphate. Okay. If it says potassium phosphate and it wants you to write that down, that's the one on the bottom here. Okay. What's potassium? Potassium is K, right? Which is right here. That's potassium. Phosphate is PO4 3-. Okay, that's phosphate. So potassium has a +1 charge because when it's ionized, it'll have a +1 charge. So how many potassiums do we need to balance out the charge with phosphate? We would need 3. So we would have K3, put this one in parentheses, PO4. Okay, potassium phosphate. That's what this would be. Okay. Um, cool. Let's do, why don't you just draw out the rest of these quick 1 through 5? Practice drawing those out. Okay. So lithium bromide, cobalt chloride, sodium hydroxide. Okay. I'll give you like 30 seconds and I'll get a covalent ones we can go over. Okay, let's do it. I'll go through these kind of quick just because I want to give you practice. I want to get through more topics. So lithium has a +1 charge when it's ionized. Bromide has a minus charge. So lithium bromide. Pretty simple. Cobalt, it tells us that it has a +2 charge, right? Chloride is Cl minus. So that means we would need 2 chlorides to bounce out the charge. So CO um, Cl2. Okay. Sodium hydroxide. Sodium is +1 charge. Hydroxide, that's one of our polyatomic ions, OH minus. Okay. So sodium hydroxide is NaOH. Okay. Chromium, if you have questions on any of these, say so. I'm just going to go through them. Okay. Chromium chloride tells us there's a 4+ charge. Okay. So chromium 4+, chloride is minus. So we need 4 chlorides to balance it out. So CrCl4. Okay. 5, sodium Na plus, sulfate, that's SO3. I don't know why I keep forgetting this. 2 minus. Okay. To balance this out, we need 2 sodiums. So Na2SO3. Okay. Sodium sulfate. Cool. Any questions on those?
I just want to make sure that I have sulfate written down right, but is it SO then 4 2 negative or SO3 2 negative?
It's 4. Sorry, I was just checking because I wasn't feeling super confident. It's
No worries.
I'm reviewing this stuff too. I took this class a while ago, but well, I took 105, but it's the same thing. But yeah, SO4 2 minus. I'm really sorry. Hey, you know it better than I do, so good for you. That's really good. Sweet. Let's keep going. Let's do, I got a list of things we can do some naming with. I need to practice naming covalent ones. Okay. So I'm going to do like 4 of these here. I want you to just try to name them on your own and then I'll go through them. So here's one N2O SF6 um, PCl5. So practice naming these. Okay. Give you two more just for good measure. Okay, take like 30-ish seconds and go those. Okay, let's do this. So N2O. Again, the rules for these start with the first one first, or like often like the official rules are like least electronegative atom first. Usually it's just the first one. And you're not going to be given super complex naming. So least electronegative goes first. And then you always use the suffix on the second atom and then prefix on both of them. Except for, let's do this one. Let's do HBr because this one, I went over this in my review a lot, but just to make sure you guys remember. So dinitrogen monoxide. Okay. Two nitrogens, one oxygen. Here we would have sulfur. Yeah, sulfur hexafluoride. You're noticing here probably that because if there's only one first one, we don't use mono. So just sulfur. We never have mono at first. So sulfur hexafluoride. Phosphorus, pentachloride. Okay. Dinitrogen, pentoxide. This would be dichlora. Wait, is it? Sorry. Dichlorine. Chlorine. Oh. Monoxide. Sorry, I'm checking myself really quick. I'm having hesitation. Okay. This is right. Dichlorine monoxide. Okay. And then this, so this is the one where like HBr, if you see HF, HCl, this applies to all of them. It would be hydrogen bromide, not bromide. Bromide. Hydrogen bromide. So you notice we're not using a mono here. With these ones, we don't use a mono because it doesn't really need to be distinguished. Since it's just a hydrogen, we know it's like there's only one. It's just hydrogen and one. There can't be like two bromines here. So they're kind of, and also these are so commonly used. This is just the name for them. So hydrogen fluoride, wow, hydrogen bromide, hydrogen chloride, hydrogen fluoride, not hydrogen bromide. Okay, remember that. Cool. Any questions on these? Sweet. You guys are doing great. We're almost ready. Almost ready for the test. Okay, lattice energy. Some of you wanted to do lattice energy. Let me explain to you really briefly what this is. You don't really need to know, but just like so you can remember. Lattice energy is basically a value that says how strong an ionic bond is. So when sodium and chloride come together, they form a really, really strong bond called an ionic bond. Na, here's the really, really strong bond, right? Cl, they're bonded to each other, super strong ionic bond, okay? Um, the energy that this bond, basically like how strong this is defined by our lattice energy. It's technically the energy that it takes to break this bond, because that's how strong it is, like the energy it would take to actually break this bond. But if it has a lattice energy of like 1,000, then this would be like that's pretty strong lattice energy. Okay. So that's kind of what it is. And then I guess what's going to happen is here's sodium, here's chloride. It's like a little smaller ball. They bond together like this and they form this lattice structure that looks like this. Lattice, because if you know like what a pie is, like well, I'm sure you don't know what a pie is, but like the lattice top on a pie where it's like you have the pie and then it's like this pattern where you have like the ones that go up, the ones that go down. That's like a lattice design. So it's the lattice structure because it forms a structure that is similar to that. You have like this, kind of like a checkerboard. Okay, so this is the structure that is formed when an ionic compound comes together, like NaCl. And this forms this crystal, like strong, like hard structure, which is typically a salt. That's why table salt, this is salt, NaCl. That's what salt is, and it forms this, which is NaCl. Okay, so that's what lattice energy is. The energy, the stronger, like a stronger energy, like what this problem says, is it's related to charge and distance. Okay, so a higher charge means a stronger lattice energy. Okay, so in this case, if it was a charge of like magnesium bonding to chloride compared to sodium bonding to chloride, sodium has a plus, sodium has a +1 charge, magnesium has a 2+ charge. So this is going to have a stronger lattice energy than this will. Okay, because it has a higher charge. And this will have a lower lattice energy. It will be weaker than this one because it has a lower charge. Okay, and we're talking about overall charge here. So like if this is like -1, +1, and then this is like -1, even though they bounce each other out, if the higher the charge numbers are, so like we have a 2 and a 1 here and a 1 and a 1, this is going to be stronger. If we had a 2 and a 2, like if this was oxygen with a 2-, that would be even stronger because we have more charges, right? So that's the pattern here with charge. Distance has to do with size. So like the atomic radius, how big an atom is. The smaller an atom is, like let's say we have, let's go through this example. I'll let you do that yourself. So chlorine, let's say there's these ones bonding to chlorine. Okay. Chlorine, I'm going to make it smaller. This is chlorine. Okay. And let's say we have calcium, magnesium. Remember that remember the trend for atomic size, it goes left. Here, I'm gonna make this bigger. Left across the periodic table and down. So these are the biggest, these are the smallest. So fluorine is tiny, this one's big. These are like sodium is going to be bigger than magnesium, but potassium is going to be bigger than sodium because it goes down. Okay, so like if we're looking at these ones, magnesium is this big, calcium is this big, strontium is this big. Okay, those are our sizes. So we have magnesium, which is this big, calcium, which is a little bit bigger, strontium, which is a lot bigger. Okay, this one is going to have the strongest charge. Okay, so I'm going to do like 3 arrows. That's going to be the strongest. These two, since it's a little bit bigger, there's more size, so this bond is a little bit longer. It's going to have a strong bond, but it's going to be less Okay, and this one's going to be the least because it's the biggest. There's the most room between like the bond. It's the biggest bond, so it's going to be the weakest. Okay, so that's lattice energy. That's all you need to know. And this practice problem is a really good um, sorry, I'll bring that back in case you need it. But this practice problem is a really good example of what you might see on the test. Kind of the length you need to know. Okay. Um, I just realized there's like these numerical values for this. Basically, we're comparing these two compounds and saying which one has the highest lattice energy, which one has the lowest lattice energy. Okay, and remember it's based off of size and charge. So let me get you your values here. Again, this is just on the practice quiz too. So, okay, so here's our values, the values that it gives you in like the box. Try right here. So 910 kilojoules per mole. That's a lattice energy. 1030 kilojoules per mole. And then 808 kilojoules per mole. Okay. So these are sweet. So these are our three lattice energies. Basically, now we're just matching them, like which one goes along with which of these. Which one is lithium fluoride, which one is sodium fluoride, and which one's potassium fluoride. So figure that out, match them up really quick, and then I'll go over it. Okay. If it doesn't make sense what this question is asking, then ask me. But okay. So again, let's look at the trends here. Remember, I said it's based on charge and distance. The strongest lattice energy, so this is the highest lattice energy, is going to be the molecule that has the highest charge, and that is the smallest. Okay, they all actually have the same charge because lithium, sodium, and potassium all have a +1 charge, and then the fluorines are all -1. Okay, so we're only looking at size here. And as you can probably tell, it's just comparing the sizes. We have lithium, which is the smallest, sodium, which is a little bit bigger, and potassium, which is the biggest. So the strongest one is going to be the one with the smallest size, which is lithium. So this is going to be lithium fluoride. The next strongest one is going to be sodium. So 910 is sodium fluoride, and then potassium fluoride is the weakest. Okay, that's lattice energy. Cool. Does that make sense? Any questions? Okay, let's see. Lattice energy, naming. So we went through polyatomic ions. We went through lattice energy. The only other thing you guys mentioned was hybridization. Okay. So let's do that. Hybridization. I have a few practice problems on this, so this will be good. Okay. So I'm just gonna do practice problems for these, and then I can explain what we're doing while we do it. Hopefully, all of you have a good idea of what hybridization is, because it's kind of complex. Just please ask questions. If you don't understand what I'm talking about, then ask questions. Okay. One new message. Can you go? Yeah, I can go over polarity. I'll do that after. Okay, so hybridization. First, here's your problem. Draw Lewis structures. I'm going to give you a few compounds. This is what I want you to do. Draw Lewis structures. Tell me its hybridization. The central atoms hybridization. And molecular shape. Okay. And then how many sigma slash pi bonds. Okay, makes sense? That's what I want you to do. So here are your compounds. I'm giving you kind of trickier ones here, but if you can do it, then I think you should feel pretty. Once you finish, just like send a thumbs up or something in the chat, just so I know when a few people are done at least, so we can, and I'll go over it. Okay, I'm gonna start going over them. Um, just for time's sake. Unless does anyone want more time? Text in the chat if you're like, no, I need more time. Okay, let's do it. So first one, C2H2. So first drawing Lewis structure. This one, we have two carbons bonded to each other, so we know the carbons are going to bond. And then the hydrogens are drawn on the outside. It looks like this. This is the Lewis structure for this one, okay? If you want me to explain how to get that more, let me know, but that's a Lewis structure. Right, it's hybridization. It's hybridization. There's not a central atom, but these two have the same hybridization. So let's look at the carbon. The hybridization of the carbon and is sp. Okay. And then its molecular shape is going to be linear because anything that's sp is going to be linear. So this is just in a flat linear shape like this. Okay. So the way to find hybridization, remember there's like really you're looking at like what's it called? Oh, sorry. What's happening? I keep forgetting. I forget the term. Like electron areas. I look at like one, how many really just like electron areas do you have? Which includes like bonds, like bond areas and lone pairs. Okay. And then the number of those is how many hybrid orbitals you need. Okay. So if I need this one, it has two bond areas. This is one bond area. This is the other bond area. So it's going to form two hybrid orbitals. Okay. Yeah, so two hybrid orbitals. So if I draw this, I'll draw this out for you, just kind of explain what this looks like. So for carbon, let's look at its electron configuration. 1s2, 2s2, 2p2. This is what its electron configuration is. These are its valence electrons, okay? Because it's the second shell. There's two electrons in an s orbital, two electrons in a p orbital. Okay, so these are all the, if you draw the box notation, it looks like this. We have 2s with one box and then 2p with three boxes. Okay, 1, 2. Okay, so there's 1, 2, 3, 4 orbitals. Each of these boxes is an orbital. So if I draw it out like this, here's its s orbital, and then it has 3 p orbitals. Okay, so this is the orbitals that carbon has. In order to form a single bond, it has to hybridize these orbitals. It has to form hybrid orbitals. So what's going to happen is it's going to take, in this scenario, it's going to take its s orbital and its p orbital, and these two are going to combine to form two hybrid sp orbitals. Okay, which just looks like this. They're like these weird looking balloon orbitals. If you watch my review, I went over this in like the exact same way. And then the other two orbitals available are just going to be its regular p orbitals. Okay, so this is like, these are the orbitals that are around carbon in this molecule. It's sp because we're taking one s orbital and one p orbital, sp. Okay, that's like the recipe for our hybridization. Okay, and these orbitals, it's like they're just mixing together to form a new weird looking orbital that is used to form a single bond. Okay, so in this molecule, sorry, Carbon uses one of its hybrid orbitals over here to bond with hydrogen. It uses the other hybrid balloon orbital over here to bond with the carbon. And then the other orbitals it has are its p orbitals. So I'm going to draw them like this. Okay. This is looking weird now, but like here's its p orbital. I'll draw them in different colors. That might help. Here's one p orbital. Here's the second p orbital. Okay. These p orbitals are used to form the pi bonds, the triple bond. Okay. The hybrid orbital is only for the single bond because like we have carbon bonded to carbon. We have one bond right here. I guess I like to think of it like here is our hybrid bond. It's black. This is our other pi bond, and then this is the other pi bond. Okay. And that's what these orbitals are used for. They're used to form the triple bond. Okay. So the carbon on the other side has the exact same configuration. It also has the same orbitals. So it has one of these balloon orbitals here, and this is where like these are bonding. And then it has its other ones, its other p orbitals like this. Okay. And then these two bond in like this circle like this. Okay. And then these two bond like this. And that is where your triple bond comes from. That's what that is. Okay. Really weird, but that is what hybridization is. It's really just like what happens to the orbitals to cause them to bond to other atoms. And this is what happens. They hybridize to make a single bond. And then if there's more bonds, then they use their p orbitals. Okay. Any questions on this? Does that make sense? Yeah. I explained this in the review. So hopefully, like if you watch that or if you already have a good idea of this. I just felt like I should just explain this because it helps understand where hybridization is coming from and like what it even means. Okay. So that's going to be this one. Hopefully you got that right. If you didn't, now you know. Let's do this one. Actually, okay, yeah, let's do this one. This one, I'm looking at it now and I'm like, oh, we didn't need to do this. This is a little more complicated than we need to because you don't need to know this deep. So if you got it right, great. If you don't know how to do this one, don't worry about it. Because this would be oh wait, actually, let me make sure. Oh, wait, phosphorus. That's 1, 2, 3, 4, 5. Oh, yeah, table go. Phosphorus one. Oh, okay, never mind. We're good. 1, 2, 3, 4, 5. Yeah, okay. Sorry, I was overthinking this. So here's our Lewis structure. We would have all these atoms here, electrons here too, I mean. Like that. Cool. So this one, it's hybridization. How many areas of electrons do we have? So bonds or lone pairs. We'd have this, 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 and this. Okay, so four bond areas. Okay, this means that we need 4 hybrid orbitals in order to bond here. Okay. I'm just gonna make sure I'm drawing this right, just because, as you know, I doubt myself sometimes. Oh. Okay, sweet. I'm right. We're good. You know what's called these electron domains? That's I was reading it, and that was the word I think I was looking for, like electron domains, like an area where electrons are, which can be an area of bonds or area of lone pairs. Okay. So like I said here, it needs 4 hybrid orbitals. Okay. Which is going to be sp3 hybridized. Okay. That means that it takes its it takes one s orbital, three p orbitals, makes four hybrid sp orbitals like that. And then clean this up. And then it's sp3. Okay. So it really, this is, you don't need to know all that background info I was giving you. Really just know how to identify the hybridization of a molecule like this. You count how many electron domains there are. There's four. If there's four, that means it needs four orbitals, and that's going to be created with s, p, 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 which is sp3. One s, three p's, sp3. Okay. So its hybridization is sp3. Its molecular shape is going to be tetrahedral. Okay. So that just looks like this. We have like oxygen up here, and then if I did this in like 3D, we would have Cl, Cl, and then the other one would be like back there. Okay, so this is forming like a pyramid down here, and then we have the one straight up. So it's like this triangle looking shape. Okay. Cool. Make sense? The other ones, like to note, there's if it's sp3, like sp is always linear. sp2 is always trigonal planar, right? But sp3 can be tetrahedral. It can be sorry, I'm trying not to erase things as fast, just in case you want to write them down. It can be tetrahedral. It can be trigonal pyramidal, or it can be bent. Okay. Tetrahedral is what I just showed you, that one. And this happens when it's just only bonds. Okay. Trigonal pyramidal happens when there's one lone pair, three bonds. Bent happens when there's two lone pairs, two bonds. Okay. That's the distinction between those. When you draw out the Lewis structure, if it's four hybrid orbitals, just distinguish between these, and that's how I tell the shape. If you want me to go over what those look like or examples of those, let me know. But if not, I'll just keep going. Okay. BH3. This is the Lewis structure, three H's. This is chill because boron, yeah, has three valence electrons, 1, 2, 3. It's 1s, 2, 2s. Wait, no, 1s2, 2s2, 2p1. Okay, that's the electron configuration. And it has 1, 2, 3. Okay, so that's great. I know the octet isn't full. This is kind of another exception. It just doesn't need, like, it's stable right here because it doesn't need more electrons. The hybridization, we have three areas, 1, 2, 3. So 3 is going to be sp2 because we need one s, two p's. Okay, forms sp2. And then one s orbital, two p orbitals make sp2. Yeah, so three sp2 hybrid orbitals there, and then the shape is going to be trigonal planar, which is just like the three sticking out flat on a surface, like plane. Okay, that's that one. Last one, HCN. This is very similar to our polyatomic ion cyanide. Remember this one where you draw this? Remember? This is very similar to this, but it has a hydrogen. So this is hydrogen cyanide, actually. So instead of a charge, it just has a hydrogen on it, which is just bringing it's bringing a proton in to balance off the charge. Okay. So here's the Lewis structure. We have H bonded to C, which is bonded to N, like this. Okay. And the hybridization on C, we have 1, 2 electron areas. So it's going to be sp, which is a linear shape. Okay. I just realized I did not count the pi bonds and the sigma bonds. So let's go on the top and count those really quick. So we have C2. Oh, wait, sorry, I'll draw this out. HCCH. Here's the first one. We have 1, 2, 3 sigma bonds, and then we have 2 pi bonds. Okay. This one right here, we have 1, 2, 3, 4 sigma bonds, and then we have 1 pi bond. And the only way you're going to have a pi bond is if you have a double bond or a triple bond, because that's the only time they're actually formed. Single bonds are always sigma bonds. A double bond, the second or third bond in the double bond is going to be a pi bond. Okay, so these two are pi bonds in this one, and then this one is a pi bond. Okay. In this, we just have 3 sigma bonds. We have 1, 2, 3. Same. Okay, and then this one here, HCN. Okay, we have 1, 2 sigma bonds, and then we have 2 pi bonds there. 1, 2. Okay. Any questions about what I just did here? Does this make sense to you guys? Any more questions on hybridization? I think I covered everything there that you would want to know. One like note to remember too. I just showed you like how pi bonds are formed. Like if carbon and carbon are bonding, the pi bonds would like the p orbitals like this, and then the bond forms like between them like this, right? Know this and know how they're formed and know what they are and why they're different from sigma bonds. Because like sigma bonds are formed with the hybrid orbitals like this, right? The pi bonds are formed kind of outside of them. And this is where triple and double bonds are formed. So this, what I'm showing here is a double bond between 2 carbons. Okay. So know the difference between that. I would know how to draw this too. Yeah, I just remember what I'm drawing here. And yeah,